Sure. Thank you. Thanks. Good greetings, everyone. And first of all, I would like to thank all the organizers for organizing such an engaging conference and giving me an opportunity to give a talk in this conference and give my perspectives about both my work and also about gender perspectives, which is again one of the major theme of this conference. So at the background, you're observing one image, which is an artist impression of an accreting compact object or X-ray binary, to be precise. And we have a compact object which can be a black hole or a neutron star, which is accreting mass from a companion star, which could be any sun-like star. So this is an artist impression, not to scale. And in this talk, primarily, I'll be talking and focusing about these class of objects. And so, as I mentioned, this compact object can be a neutron star or a black hole. Now, why are we interested in studying these systems? For example, why neutron stars are fascinating objects. And as you may know, that neutron stars are really dense objects in our universe, and which is basically forming the natural laboratories where we can check basically the presence of ultra-dense in a very ultra-dense nature of the object and in a very compact environment, because you have something like city like Chicago, which is the size of the neutron star, but the density could be like if you have a teaspoon of a tea, sugar or anything, which would be almost like billions of mass on the Earth. So if you can compare it, the densities are supernuclear and the size is extremely small, of the order of 10 to 15 kilometers. And again, there is diversity of these systems because they are not only dense objects in the extreme environments, but they have also larger spin periods, they have diverse magnetic field strengths. So there are various factors which basically motivate us to probe into these systems and to understand what is the supranuclear densities existing in these neutron stars, what is the equation of state of these systems, and these things cannot be probed by any laboratory experiment on Earth, whether it be LHC. So again, as I mentioned, they are diverse in nature. So one of the way which we can classify neutron stars is based upon the magnetic field strengths. So they can be classified as high magnetic field or low magnetic field neutron stars. Again, you see the range of your magnetic field strength. This is extremely large compared to the magnetic field strength of the Earth. So again, we are talking about highly magnetized objects. So all these facts about neutron stars makes it us interested or motivated to study these systems. So how we can probe into these systems? One of the ways is to study these systems in X-ray binaries, or in a system, as the name suggests, you have two-star system. One is a compact object accreting mass from the companion star. So in the case of low magnetic field neutron stars, the matter which is coming from the companion star, it can fall onto the surface of the neutron star, which means it can hit the surface. And once this accretion process takes place, you get eruptions from the surface of the neutron star. And this is basically, again, an artist impression of a burst which is coming from in the X-ray band, because these predominantly emit in X-rays, and that's why they are called X-ray binaries. And you see these eruptions in X-ray band, which we study to understand these systems. So this is one of the ways which I'll be focusing on. And if you observe this profile, there's a fast rise and an exponential decay. So, and if you see the total duration, it would last, say, about from 10 to hundreds of seconds. And generally now I'm saying that we use this as a tool to understand these neutron stars, but how we do that? So the way we do it, we are based upon some assumptions. One of the assumptions doing the study is we believe it to be a thermal emission from the neutron star surface. And this thermal emission, as you all know, that can be fit with the black body model. And again, you know Stephen Boltzmann law, very basic physics, and you can infer the radius. I'm making it simpler, but we do have certain other factors also hidden. But this is how we basically estimate the radius of the neutron star. Of course, these correction factors, which comes because they are very far away from us, you have to correct it from redshift factors. You have, again, as I mentioned, there is an assumption of a black body. But the neutron star is has an hot atmosphere because it's accreting matter, which means it will have hot electrons also on top of that, which means that all the black body emission can go to harder emission also, which is inverse Comptonization. Again, all those factors do contribute in our estimation, so these factors have to be incorporated when you have to make measurements. And again, once you have the radius measurements and you have simultaneous mass measurements also, then mass and radius, basically, these measurements will allow us to probe into the equation of state models. And this is the way we basically use these observational tools to probe into the equation of state of these neutron stars, or perhaps to find out the composition of the neutron star. And then here, what we are emphasizing is on the observational features which we are observing in the X-ray band. And these objects, I did mention that predominantly emit in excess, but that does not mean that it is only about X-rays. So if you want to understand the comprehensive geometry of these systems, you need to observe it in different bands and at the same time, because these are highly variable objects. You're talking about accretion processes on these strong gravity objects, which are accreting at different mass accretion rates, and at the same time, they are doing this fluctuations are varying rapidly with time. So if you are observing a system at one time with X-rays, and say after 2 days or maybe a week later, you are observing in the radio or say optical, the properties will entirely be different. So they are highly variable objects. So you need simultaneity. And this artist impression basically shows you that how the accretion rates are basically causing those geometry changes which I'm talking about. For example, here it's a compact object is a neutron star, and matter is accreting onto the neutron star. And because of that inflow, and if your mass accretion rates are higher, you will expect that your basically this is the bottom part where mass accretion rates are higher. You will see that the accretion disk, which is formed around the neutron star because of this accretion, will go closer to the neutron star. So now it is very close to the neutron star, but when the mass accretion rates are lower, so they are not always accreting at the same rates, your accretion disk would be a bit receded away from the neutron star, and there can be hot flow, which could be in the form of electrons and things like that, which will be contributing to the other emissions which we observe in the broadband. So this is the need of coordinated efforts of multi-wavelength observations to study or obtain the comprehensive understanding of these systems. And yes, I'm part of this global network, which is SmartNet, which allows us to probe into these systems. Whenever there's a new transient coming up, we follow it up in different bands and looking at these objects at the same time. So this again illustrates different observatories in the multiband, which we have been using it for our work. Again, I have been part of AstroSat team and have been working since, say, later or final stages of my PhD till now. So we have really started some surveys and some other projects with AstroSat as well. In addition, I'm part of several NASA projects as well, including NICER. So where we are probing at different energies, because in X-rays we don't talk about wavelengths or frequencies, we talk about energies. So soft and hard X-rays, and here we deal it with broadbands. So NICER works in the soft X-ray band, and AstroSat has a broadband coverage, but again the LAXVC, the major component, works in the harder energy band. And it is meant for fast timing studies, which are meant with the variability we observe. So these are some of the glimpses of some results which we have obtained with AstroSat. And since this is Indian community-focused conference, I thought I should show some AstroSat results in this conference. And so these are results which came from the neutron star studies, neutron star X-ray binaries with the low magnetic field. Here the neutron star is low mass X-ray binary system with a low magnetic field. And again, this thermonuclear X-ray burst. Now this is a real light curve which we obtained from the large area X-ray proportional counter on board AstroSat, which are these red counters. And again, this is an example of an observational study that how we perform this time-resolved spectroscopy. If you are interested in details about how we do that, please come back. Just because of interest of time, I'll just move forward. So I just wanted to demonstrate that these are observations. So as I mentioned, I was right from the launch stage, I was involved with AstroSat and primarily with LAX PC. So during the performance verification phase, we discovered rapid triplet, which was like 3 bursts, which are occurring at a shorter recurrence time. Generally, we would expect or observe thermonuclear X-ray bursts separated by, say, at least 30 minutes. But here, if you see the time difference between the 2 bursts, they are very small intervals. So it is less than, say, 5.5 minutes. So this was the discovery of a very short recurrence burst. And here, this is basically the literature, which basically shows there are several hundred thousands of bursts observed so far with different observatories, but only handful of these systems show triplets. So this was one of the rarest discovery made with AstroSat. And these are the shortest wait times reported so far, but later we also reported with NewsStar, which was shorter than the AstroSat result. But at the time of AstroSat publication, this was the shortest recurrence burst, which was observed. Again, with AstroSat, it allowed us to perform detailed timing studies because the LAX PC has a larger collecting area because you saw 3 red counters, and that effectively gives you around 6,000 centimeters square of your total collecting area or effective area. Which means because I'm talking about very short bursts, and in that also we are time slicing them to perform the time resource spectroscopy or timing studies. So which means we need larger number of counts to perform, so the process does not become straightforward anyway. So with AstroSat, because of its efficiency in collecting area and time resolution of microseconds, allowed us to do detailed timing studies also. So this work was done with my student at ISA Mohali. So before joining IAA, as I told, I was in SPA faculty at ISA Mohali. So this paper led to an interesting results where we actually discovered burst oscillations, again, because these are rotating neutron stars, and we would expect to observe the spin frequency of the neutron star. So that spin frequency of the neutron star is not always observed during the thermonuclear X-ray burst because it can rapidly fade away because of it could be lack of the count rate, because we are talking about, say, 0.5 second time of the total burst. So we may not even detect it. So they are not always observed, but we detected burst oscillations during these thermonuclear X-ray bursts with LAX PC. And again, one of the interesting results, which you may not appreciate right now because of the lack of the understanding of the models perhaps behind that, but we discovered high fractional amplitude burst oscillations during the decay phase of the burst. And I would happy to discuss why it was an interesting discovery, maybe during the Q&A. So then again, we started a survey after we gained confidence that we can perform detailed timing studies with AstroSat. We started a survey of looking at all the transients and doing the fast timing studies and to either look for burst oscillations or thermonuclear X-ray burst. And during that survey, we observed this particular neutron star during its outbursting phase. And this is LAX PC light curves, the 2 observations made with AstroSat during its outburst. And interestingly, this light curve, which is the middle panel here, you'll see large variability. And if you zoom in into one of the flare or variability you observe, this is how it looks like. And the second observation, it was a thermonuclear X-ray burst, and this is how the expanded view looks like. So now 2 observations separated by a few weeks or few days of time, they show different behavior of the light curve because the rest of the light curve in the second observation is almost flat, or say average count rate is almost constant. So no variability as such. And then we performed the detailed timing studies, which means the time slicing the flares and also the thermonuclear X-ray burst. We discovered burst oscillations as well as accretion powered oscillations. So the burst oscillations or the type 1 burst, the origin is observed to be the thermonuclear runaway processes. It's not a gravitational energy release. While in accretion powered, you will expect the gravitational energy release, which is observed in the form of X-rays. So we observed, sorry, there's a typo here. So these are not burst oscillations, because once in one observation we saw flares, and the second observation we saw thermonuclear X-ray burst. So flares are gravitational energy release, and bursts are thermonuclear runaway processes. So observing that at almost consistent frequency, it allowed us to discover a new system, which is accretion-powered millisecond X-ray pulsar. So in the class of neutron star X-ray binaries, and especially in low-mass X-ray binary system, where we have a subclass, which is accreting millisecond X-ray pulsars, and although we know hundreds of neutron star X-ray binary systems, there are only handful of such systems, only 25, including this one with the new discovery with AstroSat. So you can imagine that with a larger collection or larger population of neutron star X-ray binaries, we only have 20 or 25 of such systems. So that discovery really contributed and came out from AstroSat, which is our own Indian mission. So again, we did some broadband spectral fitting also, with including NewStar, which is NASA mission, and AstroSat observations, which are shown here. This red and black are the NewStar observations, and doing that broadband, you can compute the flux, which is required in calculating the magnetic field, where we are assuming, because of the magnetic field strength of the neutron star, matter is channeled onto the neutron star, and hence using that assumption or plausibility, we can estimate the magnetic moment and hence the magnetic field of the neutron star. So coming to the last part of the talk, where last part of the science talk, where we are talking about the multi-wavelength coordination to obtain the deeper insights. I mentioned about the requirement of the simultaneity, and this is, what did I do? Okay, sorry. Yeah, so these are not X-ray light curves, these are optical light curves. And for a particular black hole X-ray binary system, although when this system was discovered, we didn't know what is the compact object, but the optical light curve, something looked like this one. On the top, it's like a long light curve, and then you zoom in into this part and you see, and you observe in the optical band, there is some sort of dipping behavior. Some variability patterns were observed, and these people reported in Science, they performed these periodogram studies, and they observed a frequency range observed at, so the range of frequencies which they observed is varying like this. So this is frequency, and this is time plot, and the frequency was evolving during the outburst. Basically, the frequency was decreasing with the time, and basically it means the peak of the outburst was highly spinning black hole, and during the decay phase, it was declining. So, part of this studies, they proposed different plausibility, and one of the plausibilities of observing this tipping behavior in the optical light curve would be the presence of obscuring medium in the accretion disk, which is causing that absorption in the light curves. And if that is the case, if you know about the Aegean geometry also, we have a plausibility of having a torus, and which basically called obscuration in the X-ray band. And if that is the case, because of the reflection of the disk, you would expect to observe an iron line or a Compton hum, which are the features of the reflection in these class of systems. So based on or motivated by those facts or plausible explanation of their optical observations, we proposed multiband observations with X-rays optical in the optical band with ultracam. And with X-ray, we had NewStar and Swift observations. With the NewStar, we have this broadband coverage, which can probe into the iron line and also the Compton hump. And when we looked at the observations with NewStar, surprisingly, there was no signatures of an iron line or Compton hump. and which is kind of not supporting the fact of having an obscuring structures in the accretion disk. And this, but if we look at the optical light curves, we basically saw almost a similar behavior we observed in, say, 2011 outburst, which was the first outburst in this source. However, these are 2017 because after 6 years of interval, it underwent a second outburst. Yeah. So then again, this is a very peculiar source, again emphasizing in 2021, we again had another multi-band set of observations with NICER now included because there were several open questions remain for this system to understand. And we discovered with NICER, again, the QPOs, which were consistent in the frequency observed in the optical band. Again, become a challenge to explain why these QPOs also exist in X-ray and also in the optical band simultaneously. Again, we had come up with this, some understanding of this system, where we believe that there may be an obscuring structure, but the X-ray is coming from this hot electrons which are above the neutron star, black hole in this case. And that is why we do not see any reflection features, because it's not reflecting off the disk, but the hot electrons are contributing. Now, finally, since the conference is themed on gender perspectives, so here are my views about how, or rather challenges which I may have faced, or I have faced, I would say. So journey of a scientist who is a woman, and of course, we dream big, we have our own, that's why we are here in this astrophysics community. But what happens, because we are motivated, we are inspired, and we want to pursue our research, we do everything that is needed. We will publish, being a PhD student, we will publish papers, we won prestigious fellowships, and we also do all job or responsibilities as one would expect a faculty to be doing. It could be mentoring, it could be teaching, it could be taking part in extracurricular activities, but then road is closed for us. Is this like yesterday also we were having discussions that and some of my friends have also faced the same question, like after doing so many postdocs, where are you heading? You're not getting a job. So, which is kind of a road closure, but again, now we also think that academia is not only the end of life, you have alternatives, but still, there are some stereotypes. So again, this is an example of leaky pipeline. We have a good ratio, gender ratio in the initial phases, but towards the higher stages, we end up having very limited or very few people. So again, based upon all the challenges faced by people and requirement or the need of the hour, so we had a conference in Hyderabad also, which was organized by Prajwal, and it was my pleasure to be part of that workshop and conference. We also had different activities, and again, a very important document which resulted out of that conference was Hyderabad Charter, where discussions were not only within the community members, but including sociologists, other people from the entire community, which are giving their point of view as well about what the change is required or what policies should revise to have more inclusion. So I would really encourage you all to go through this page, IPA page, and where you could find this document. It would be nice to even endorse it. We do have Google form where if you are interested, we can circulate it for your endorsement and support. And again, yesterday we had discussions about hiring processes and transparency. So all these are sort of documented in that document as well. So perhaps it would be nice if people can have a look and provide their feedback and in fact support if possible. So again, I'm a part of WGGE group. Again, Preeti, thanks to Preeti and people who actually initiated this group as part of the Astronomical Society of India. And again, after this constitution, there have been several changes which are visible and we have observed. And again, Anamani lectures is one of the kind of series of lectures which WGGE has been organizing regularly, almost twice a year. and where people can actually participate, and also these speakers are not again scientists or from the astronomy background, they are from the wider background. And again, this was based upon the gender fractions which we observe. I will not take more time on talking about it, but now I would like to really emphasize, please join for the upcoming Anamani lecture organized by IAA and WGG together. And this will be on 11th of November, and this will can be joined as an online event as well from the YouTube link. So I would be happy if more participation comes from this conference people. And yeah, so another group is Karina's, which is again in sort of semi-informal group, because here we have this group was actually founded by these members, Prakriti, Manami, and Sanskriti. And you can see here, you can contact here if you would want to become the part of this group. Again, this is a semi-informal group discussions with different stages of people at different levels of their academia. And it helps us in taking out what we are feeling. So we really support each other in that way. There is a mentoring and mentee process also, program also as part of Karina's, where basically you can help each other in guidance, help, or any way possible. Again, this is the web page, and it started with the 3 members. Now we are 250 current members, and they are from different parts of the globe. And again, this is the mandate to empower the early career women researchers. And again, you can read about it. And that's all. Sorry if I've exceeded time.
Thank you, Aru. We've run out of time for questions, but I would still like to take maybe one quick question.
Thank you for a very nice talk, Aru. So I was a science question actually. So for this triple burst that you said, so what really determines the recurrence time? So why is it rare, this?
So there are different understandings about it. For example, if there's a thermonuclear runaway processes which are causing these thermonuclear exobursts, and which basically means that entire accreted matter should be depleted after the burst is washed away, like it has gone off. But apparently there are different plausibilities in the literature which do explain or partly explain the occurrence of these short recurrence bursts. One of them is short wait time, which is based on the nucleosynthesis process. Again, these nuclear energies which are released in this nuclear reaction networks, the people believe that the wait time between the 2 nuclear reaction networks is such that it's smaller, and that is why it ignites the second set of reaction which is releasing the energy. But this theory does not explain the observational features, which is the intensity which we observe, even the time scales is not matching up with what they have computed in the nuclear part, with respect to the nuclear physics. But then again comes another plausible theory, which is based upon there could be some sort of leftovers from the previous burst, and which is brought to the right ignition depth at right temperatures by convection. And that is causing the ignition of the second. And this plausible theory is basically explaining the intensity and the wait times also.
Very interesting.
There are some exceptions to, there are some exceptions again, which is intriguing to that theory as well.
Yeah, thank you. Thank you, Aru, for the gender equality part as well. I'm sure there are many more questions, but in the interest of time, we will now move on, but we'll keep the discussion going. So we'll move to our next speaker.